Hello friends, welcome to Simply Chemistry. In this video, you're going to see what are chiral carbons and assign the absolute configuration or the RS configuration. A chiral carbon is a carbon which is attached to four different groups. You could see this example. So you could see these four groups are different, hence this carbon is chiral, which is generally represented using a asterisk mark. I've given an example for a chiral carbon. You could see that this carbon atom is not attached to four different groups. Such carbons are referred as achiral, whereas if a carbon is attached to four different groups, we call it as a chiral carbon. What is speciality about the chiral carbon? They have the ability to rotate the plane polarized light, and they give rise to stereoisomers. We call them as enantiomers. Enantiomers are nothing but non-superimposable mirror images. So I have drawn the mirror image of this molecule over here, and you could see that if you try to place this molecule over this, it becomes non-superimposable. It is not the same. That is what I mean. Hence, it is an enantiomer. So the maximum number of stereoisomers possible for a given molecule is given by the formula 2 power n, where n refers to the number of chiral atoms. So in this case, it is 1. So the number of possible stereoisomer for this molecule is 2. So this is 1 and this is 2. Here I have given some examples for starters to find out the chiral carbon. So in this molecule, we have a chiral center here and a chiral center here. There are two chiral centers, hence the possible stereoisomers are 4. Likewise for this one, we have 1, 2 and 3. So we have 3 chiral centers, so the possible isomers, stereoisomers are 8. Though figuring out the chiral carbon looks easy, assigning absolute configuration is tricky. Let us see how to assign the RS configuration for a given Fischer notation. Step 1 is to assign the atoms that are attached to the chiral carbon based on their atomic number. We have to assign priority based on their atomic number. So you could see this example where here the bromine has the highest atomic number, so it gets number 1, followed by chlorine. This carbon atom is attached to carbon atom, so this is 3, and the least priority is for your hydrogen. So you also have to check that always the least priority group should be projected away from you, or in other words, in the Fischer notation, it should be at the bottom. If it is at the bottom, you can directly go on finding the RS configuration. In this case, it goes via this direction, 1, 2, 3. It is anti-clockwise, hence it has S configuration. Similarly, let us try assigning the RS for its corresponding stereoisomer. So again, we are numbering them 1, 2, 3 and 4. You could see 4 is at bottom, that the least priority group is already at bottom, so we don't have to bother, just go for finding out the way it goes. So it is clockwise, hence the configuration is R. You could see that if a molecule has S configuration, its corresponding mirror image will have its opposite configuration. So let us see an example where the least priority group is not at the bottom in the Fischer notation, or it is not away from us. So again, we have to go for numbering. So we have to number 1, 2, 3 and 4. Our objective is to bring the least priority group to the bottom. So here what we are doing is we are going to bring the least priority group bottom. So I'm exchanging these two groups, so we get a species like this, that is bromine goes to the left side, hydrogen comes down, CH3 and Cl stays at the same place. We cannot assign just by bringing it down with one single change. When you try to transfer, or when you try to bring the least priority group to the bottom, we have to make two changes. You could see here, so we have to take any other two more changes. Either you can do this or even do this. Both will lead to the same answer. We'll see both of them. So you could see this will lead that if you exchange bromine and chlorine, this is gonna yield this structure. So we have made two changes. Now we are going to assign the RS configuration. So this is going to be number 1, 2, 3 and 4. You could see that it is going on the counterclockwise direction. So the assigned configuration is yes. So let us try exchanging these two groups. So we will get the chlorine will be at the top, bromine will come to your right side, and CH3 to your left side, and hydrogen at the bottom. So again we go for numbering them. So you could see that 1, 2, 3, it is again in the counterclockwise direction. So the assigned configuration is yes. So let us see few more examples. So this is another type where we have to assign the RS configuration for the wedge and dash notations. So first I will explain how to convert the wedge notations to the Fischer notation. Then we will see a simple trick to find out the assign the RS configuration without converting them into the Fischer notation. So let us see how to convert the wedge notation to the Fischer notation. So always remember, the group that is projected behind will be at the bottom of the Fischer notation. So if you view this molecule from this direction, you could see your chlorine is at your left side, bromine is at your right side, and iodine is at your top. So let us assign the numbers. So this is 1, 2, 3 and 4. So in this case, the least priority group is already at the bottom. So we're going to find out the configuration. So it is going along the clockwise direction. So the assigned configuration is R. So let us see for this one. So we are going to view the molecule from the same direction. So in this case, your chlorine will go to the bottom because it is behind. You could see the dashed lines. That represents that the atom is projected away from you. On your left side we have fluorine, on your right side you have bromine, and at the top we have the iodine. So now if you assign the numbers, that is 1, 2, 3 and 4, these are the numbers. So now our objective is to bring the least priority group to the bottom. So we have to make two changes. So I'm trying to interchange chlorine and fluorine first. So we get this. So iodine stays at the top, bromine here, chlorine and fluorine. So we have made the first change. So we have to make the next change. I'm exchanging iodine and chlorine. So we get chlorine goes to the top, iodine is here, bromine is at your right side, and fluorine. Now go for assigning the numbers. We already know that 1, 2 and 3 and 4. You could see that it is going on the counterclockwise direction. So the assigned configuration is yes. Exchanging the atoms is little confusing. So I am suggesting a method without exchanging the atoms. We can easily draw the Fischer notation. So you could see this molecule that the least priority group, that is, we will assign the numbers 1, 2, 3 and 4, sorry, 3 and 4. The least priority group is not projected away from us. So what I am suggesting is that to go make this from this side, it is easy to do if you rotate along this direction, this axis, this direction with the angle of 120, the molecule itself gets converted into like this, and just drawing it. So you could see that fluorine goes to the position of the chlorine, chlorine comes to the position of bromine, and this to this. The simple exchange of the species takes place. Still our objective is satisfied. Now if you draw the Fischer notation, you could draw it. So fluorine goes to the bottom, bromine on your right side, chlorine at your left side, and we have the iodine. So let's go for numbering. 1, 2, 3 and 4. You could see that it is going clockwise. The assigned configuration is R. So let us try to implement the rotation for the next one. You could see that now the least priority group is at the top. So we cannot use this angle or this axis for rotation. So why don't we try for rotating along this axis with 120 degrees. So this group comes here, this comes here, this goes at the top. So I'm just writing the rotated one. So fluorine goes at the behind, iodine goes to the top, chlorine is here, and bromine is here. So we know the numbers, that is 1, 2 and 3 and 4. So even from here itself you can find it out that it is going in the counterclockwise direction, hence the assigned configuration is yes. Even if you want to draw the Fischer notation, I encourage the beginners to draw the Fischer notation. It will be easy for us. So 4 is already projected down, so 3 is here, 2 is here, 1 is here. So you could see that the direction is counterclockwise, and it is yes. Let us see few more examples. So now we have learned how to assign the RS configuration. So let us try applying to the molecules. So let us see with the first example. You could see that there is only one chiral center. So you should assume that a hydrogen is projected behind. So let us give priorities first. So you could see that this case it is attached to a carbon, this case attached to a carbon, whereas this is oxygen, so it gets the first priority. As usual, hydrogen gets the least priority. If you compare between these two carbons, this carbon is attached to carbon, hydrogen and hydrogen, whereas this carbon atom is attached to carbon, carbon and hydrogen. So this has more weightage, so it gets the second priority, and this gets a third priority. So I already said, even with this you can easily find out it is having the R configuration because the direction is along the clockwise. Even with the Fischer notation you will get the same. So your number 4 goes down, 1 is here, 2 is here and 3 is here. So you can see that it is going on the clockwise direction. It is R. In the next one we have two chiral centers. You can see this is the first chiral center and this is the second chiral center. So here the hydrogen is projected away from us, whereas here it is projected towards us. So let us solve them one by one. So let us start with this chiral center, this chiral center. So now imagine we are looking from this direction. We're going to assign the priorities. So all of them are carbon. This carbon atom is attached to bromine, so this gets number 1, this gets number 2 because this is attached to another carbon, this gets 3, as usual hydrogen gets 4. So now if you go for circling, you could see that it is 1, 2, 3, it is counterclockwise, hence the assigned configuration is yes. Even if you draw the Fischer notation, you'll get the same. So number 4 goes to the bottom, 1 here, 2 at the top, and 3 here. So you could see that it is having the counterclockwise direction. The assigned configuration is yes. Let us go to the next chiral center, this chiral center. So let us assign the configuration, like the priority for them. So here this gets the first priority, followed by this, this, and this. So imagine you are viewing the molecule from this direction. You could see that if you see it from there, your 2 goes to the top and your hydrogen is at your left side, and number 3 is projected onto the right side, and bromine is going behind. So we could see it that this is the arrangement. Now it is simple for us. You can go for rotating the molecule. So obviously you will land up in this arrangement. So the groups will interchange. Bromine comes here and hydrogen goes behind. 2 is at the top. This is number 1. So you can see that 1, 2, 3. It is again going in the counterclockwise direction. So the assigned configuration is yes. So some may wonder, what if I view the molecule from this direction? Will I get the same configuration? Yes, definitely you'll get the same configuration. In that case, I'll use a different color, so it will be easy for you to view it. So from this direction, if you view it, your number 3 goes to the top, and bromine as usual at the back side. You could see that your hydrogen now it is projected to your right side, and number 2 is at your left side. So again simple. Now we go for rotating it. So we will push the hydrogen behind. So number 1, that is bromine coming here, 3 stays on the top, and 2 is here. You could see that 1, 2, 3 along this direction. So it is going to have the same S configuration. So let us see a few more examples. This molecule is easy to deal. So always remember, if something is projected up in the plane, that it is means that it is projected towards you. And the bottom one is actually away from you. So I'm just drawing that for you. See that it is projected towards you, and this is below you. And the same case here, the hydrogen is at the top and the methyl group is at the bottom. So there are 2 chiral centers, so we'll use different colors. So this is the first chiral center we're going to deal with. So let us assign priority for this. So if you calculate for this one, this is going to get the first priority because it is attached to 2 carbons. So this is 1 carbon, and this is going to be 3, and this is going to be 4. Now we are imagine like you are viewing the molecule from this direction. So I'm going to draw it. So as usual, 1 is going to go at the top and 4 is already behind. You could see that the methyl group is onto your right side, and number 2 is onto your left side. So without drawing the Fischer notation, you can easily draw it now, as the 4th group is already projected behind. So it is 1, 2, and 3. You could see it is anti-clockwise direction, so it has S configuration. So let us proceed to the second one. For this carbon atom, this carbon gets the first number, second priority, third and fourth. So if you view the molecule from this direction, so as usual your 1 is going to go onto the top. In this case your hydrogen is going to be onto your left side and 2 is onto your right side and 3 is projected behind. So we're going for the rotation this side, so automatically we're going to get 4 here, 1 on the top, 2 here and 3 here. So now we are going to assign the configuration. So it is from 1, 2 and 3. So you could see it that it has again counterclockwise direction. The assigned configuration is this. So I've given one practice problem where you can work it out at your own time, and I will give you the answers. You can pause the video, work out and easily find out the same. So let us see that the given molecule has 3 chiral centers. So we'll see how to work out with them. So in this case you could see that there is a hydrogen projected behind. So let us assign the numbers. So this gets number 1, this gets number 2, and it is attached to bromine, this gets 3 and this gets 4. Now if you view the molecule from this direction, so it's going to be 2 on the top, your 1 is on your left side, and 3 is onto your right side, and your hydrogen is projected behind, that is number 4. So you could see that it goes clockwise. The assigned configuration is R. So likewise we'll move on to the next one, that there is a hydrogen projected in this direction. So now let us assign the numbers for this. So this gets number 1, this gets number 2, 3 and 4. So now you view the molecule from this direction. If you do it, again the 2 is going to be on the top, this is going to be onto your left side, and 3 is on to be your right side, and the 4 is projected behind. So now if again you assign down configuration, it goes 1, 2, 3 as 4 is behind, so it is R again. So the second carbon, chiral carbon, is also R. So we'll move on to the third one. That is a little tricky one. So let us assign numbers. So this gets number 1, 2, 3 and 4. You could see that number 4th group is not projected behind. So let us first drawing the molecule. So if I'm looking at the molecule from this direction, your 4 is actually going onto the top and number 2 is going behind. You could see that bromine is actually goes to your right side and number 3 comes to your left side. So I'm going to rotate the molecule along this axis. So I'm going to, this bromine is going to go on the top, that is number 1, and it's going to be a cycle 1. So this is how it will be. That is Cl, that is number 2 is here, 1 is here, 3 is here, and 4 is projected behind. So it is 1, 2, 3 clockwise, hence the assigned configuration is R. There is another shortcut. We can do it without exchanging the species. I'll show you how to do this, but I always encourage you to convert the given wedge notation to the Fischer notation, then you assign the configuration and proceed the method. So always convert that into the Fischer notation so that you will not go wrong. So here I'm showing you how to do it. So we already seen how to get the Fischer notation from the wedge notation. So we'll assign the numbers 1, 2, 3 and 4, you could see that the least priority group is not projecting below. So you can easily do it. Now if you check the configuration as such, it is going on the clockwise, so it is actually R. As the least priority group is not projected down or it's not away from us, you just have to flip the configuration that in real the molecule has a S configuration. We can check by interchanging them, so we will interchange them, and also we can check it out whether it is working correct or not. So we have done first change, we have exchanged these two. So second change, we are exchanging these two. So we're gonna get fluorine, bromine, argon, and chlorine. So assigning numbers 1, 2, 3, and 4, you could see that it is going counterclockwise. It is yes. So again, I'm telling, I would encourage you to convert the given wedge notation to the Fischer notation. Then you can easily find the configuration. Don't worry about the position of the least priority group. If it is not at the bottom, assign the configuration, flip it. I hope you enjoyed watching this video. Thank you.